Okay, now this is going to be recorded, right? Uh-huh. Uh-huh. Well, let's see if you then can see my screen. Can you see the screen? Yes, fantastic. Thank you. So that's all good. Because I'm really nervous about this session today. Um, because my wife was teaching earlier and she had to abandon class because apparently Teams didn't work. And that is probably one of the most stressful things that happen. But so far, touch wood, apparently things do work. Hmm. And there's another unmuted. Yes, I know, Conrad. This is something absolutely unheard of. Aha, there's a lot going on in the background, and I feel very privileged. Oh, she was terribly stressed. Hello, can you please mute yourself? Brilliant. I hope it was just a shower. Okay, let's get started. It's just absolutely brilliant. Right. Where do I start? Okay. So what I want to do with you today is a little bit of, how shall I say, weird stuff. And it is about measurements with uncertainties. And you know I am harping on about uncertainties and all that stuff. But what I'm going to do with you today might look totally, how shall I say, trivial. And you might wonder what on earth and why am I going to do that with you? But please stay with me, because hopefully at the end you will say, wow, I did not see that coming. So let's stay with me. I can't see the screen. Can other people see the screen? Okay, people say they can. So I guess, Imogen, that's probably something that's on your end. So I'm not entirely sure how to address that. And please don't forget to register your attendance on Moodle, because otherwise there is clown watch going on. It's sort of the higher education version of crime watch, isn't it? Okay, so please don't forget to register your attendance. The other thing that I wanted to say is please mute yourself. Bing. And people said last time that they would like me to set up some practice questions and quizzes, right? So I heard you, amongst other things. So I've set up a website with practice quizzes. Ade, please mute yourself. So I've set up a website with practice quizzes. And there is the introduction to biochemistry. There's also BI 308, skills for bioscientists. And here are some quizzes that you can do. And I suggest that you use next week to actually each day do one quiz. It doesn't count for anything. Please mute yourself. Does it only happen in my lectures? Is that right? Oh, that's weird. So I suggest you do one quiz every day next week. It doesn't count for anything. It is just for you to see how well you understand the topic. But these quizzes are actually taken from previous exams and tests. So that is what's going to hit you in an assessment. And you are also aware that there is this practice calculations website here with lots and lots of almost unlimited questions that you can do, including some YouTube tutorials. So please make use of these things, because I set that up so that you can actually check whether you have the understanding. And are people all right if I email you later the link to these practice questions and practice quizzes? Are you happy with it? Or I will also put it on Moodle and I'll put it up on here. I know that there is some kind of email fatigue, but please have a look at these things because it's I don't know how else to communicate. So that is, I will send that out later and you can practice to your little heart's content. And obviously for the quizzes, it will ask you for your ID. That is for me sort of a little bit of a record to see who is engaging and if students have problems, because then I can set up additional workshops and help and support people. It's probably the practice calculations. There's the link. Conrad kindly posted that. The practice quizzes, I will send you the link. I will send you everything together. Okay. So what I want to do with you today is, as I said, it will be a little bit unusual and it will give you practice for some calculations. because what I want to do is, again, I want to finish this chapter with measurements and things like that. And let's say we take a sample. Yeah, we know. We just take a sample, we measure a volume, and so we have sample, let's call that sample number 1. And let's say we measure a volume in milliliter, and we have 98 milliliter, we've got 100 milliliter, and we've got 102 milliliters. Okay, so that's our sample 1. And what I want you to do now is I want you to grab a calculator, please. And I want you to calculate the mean of this sample. So what is the mean of this sample, please? Hundred what? Bananas. Uh-huh. 100 milliliter. Yep, exactly. That's right. Thank you very much. 100 milliliter is the mean. And now the next question is, what would be the standard deviation of this sample, please? Can somebody calculate that? What is the standard deviation? Do you want me to quickly do that with you? Okay. So 2 what? Bananas? Aha. Shimmick says 2 milliliters. 2 bananas. Good. So the easiest way is just simply, just as a refresher, standard deviation equals the square root, and we take the sum of the individual measurements minus the sample mean. We square it, and then we divide by what do we divide? N minus 1, exactly, because it is a sample. And the standard deviation would be 2 milliliter. Absolutely right. The standard deviation has the same unit as our measurement. That's the nice thing about the standard deviation. And we are dividing by n minus 1 because it's a sample. Okay, so that's the standard deviation. And what we can do now is we can also calculate the standard error of this thing. How would we calculate the standard error? Can somebody calculate the standard error? What would you get for the standard error? And 0.2 milliliters. That's an interesting one. Aha. 1.15. What? Bananas? You see, I'm a really mean guy. Oranges? Apples. Ah, that's a new one. Okay. Do so for the standard deviation, let's just do the first part. So we will have 98 minus 100 squared plus 100 minus 100 squared plus 102 minus 100 squared divided by n minus 1, that is 2, and we take the square root of that. Does that answer it? Good. So standard error would be the standard deviation divided by the square root of the number of observations that we have. So that would be 2 milliliter divided by square root 3, and that gives us something like 1.1547 milliliter. Yep. And again, the standard error has the same unit as our standard deviation and the measurement. Okay, so that is our standard error. And in this case, we can call this also the standard uncertainty. Standard uncertainty. And let's just simply give it also a name. Let's call it SU1. Yeah, why not? So that's our standard uncertainty. And we would usually report our measurement. Report the measurement as the mean plus minus 2 times the standard uncertainty, 2 times SU1. And the 2 actually is sort of, it's not exactly 2, it's more 1.96, but I will tell you where this number comes from when we look at normal distribution. So that would be how we report it. And you multiply it by 2 to give you what is known as the extended uncertainty or expanded uncertainty. Extended uncertainty. And this gives us sort of a feel for where most of our data would lie when we did this loads and loads and loads of times again and again. And the 1.96, as I said, I will tell you where this comes from when we will discuss the normal distribution, but most people will just simply round it to 2. So don't worry about it, but I will promise you, I will give you, I will tell you where this 1.96 comes from. So in this case, we would get 2 times 1.15. This gives us 2.3. And so we would report our result as 100.0 plus minus 2.3. So let me write this down. 100.0 plus minus 2.3 milliliter. That would be the result that we report. And obviously, we would need to indicate what this actually is, how we found this. Because when you look at the scientific literature, scientific papers, what people very often do is they will report 100.0 milliliter. So 100.0 milliliter, which is, of course, not good because we need an uncertainty. And I told you, we need an uncertainty for basically all the measurements. But they will report that in scientific journals. Or they might report as 100 milliliter plus minus the standard deviation. They will, lots of people do that, even in scientific journals. Or they will report 100 milliliter plus minus the standard error. The correct way actually is 100.0 plus minus 2 times the standard error, as we just done it. But as I said, you will find all these things. And this drives people who are proper scientists, drives people absolutely crazy. And I know a colleague of mine totally flipped out. He used to be the editor of one of the big scientific journals, and I worked with. He visited our lab where I did my PhD, and in 2013 he totally flipped out in public, saying, you know, what people produce in journals is just absolute rubbish, because they never indicate what this uncertainty is. And this is really difficult and annoying. I mean, this was when, after he received the Nobel Prize for physiology. The guy is called Randy Sheckman, and he got so irate. He put really a big rant up. But I see his point. If people don't say what they report, how can you do proper science? So my suggestion is we report 100 plus minus 2 times the standard error in this case. And then we say we have a coverage factor of 2, which gives us 95% of our result. That's a 95% confidence interval. And we would usually put in normal for a normal distribution. And I know we haven't covered that, but that would be the gold standard of reporting. And that would make it absolutely clear to everybody what we are talking about. So, and the sooner you start with that, that would be the ideal case. Why I did write SU1 before, that is as the standard uncertainty. And I wanted to give that a name because I will use that in a moment again for some slightly different purpose. So very nicely observed. What is K? K is the coverage factor. That is this 2 by which I multiplied this standard error here. That's this K. And we would usually not have it. We would usually write it as plus minus 2.3 milliliter here. So people would not necessarily see this 2. Okay. Is it always 100? Well, here's is a good question. So let's do another sample. Let's do a sample 2. Sample 2. We take another sample of another volume. And let's do some gentle numbers. Let's say 39 milliliter, 40 milliliter, and 41 milliliter. Can you please calculate for me X bar, the mean? Thank you, Luis. Yes, somebody's paying attention. Yes, that would be 40 milliliter. That's true. Can you now please calculate the standard deviation for that? S equals, no, it's not 40, it's 40 milliliter. Yep, that's 1 milliliter. And now let's calculate the standard error for this guy, for this sample 2. The standard error is, what was the standard error for that? Yep, lovely, 0.577 milliliter. So that would be actually this 1 milliliter divided by square root 3. Absolutely right. And let's call this here the standard uncertainty. And again, the emphasis is on standard. And I call this now simply SU2. There's system to the madness. And we would report this as 40.0 plus minus 1.2 milliliters, right? So we would that as 2 times the standard error, and again with K equals 2, 95% CI, and normal. That's really the gold standard. Let's stick with that. Okay. Are you happy so far with that? Not terribly challenging. You just have to do a little bit of calculation and the square root. So that's easy. It would probably be easiest to write it as a decimal. The standard uncertainty in this case comes from this standard error. The standard error in this case is also what we call the standard uncertainty. Konrad, you absolutely hit it. The reason why I call it SU2 and SU1 is to keep track of the samples. And the CI, don't worry too much about it. This indicates the 95% confidence interval, but we will discuss that in more detail when we discuss the normal distribution. So I have my 100 milliliter sample. So I have my 100 milliliter plus minus, and now I just use the standard uncertainty, the standard unit SU1. So that was 100 milliliter plus minus, what was it again? 1.15 plus minus 1.15 milliliter. That was the standard. That was this standard uncertainty. And I've got 40 milliliters plus minus the standard uncertainty 2. So that's 40.0 milliliter, and we just calculated it. And that would be 0.577 milliliter. Okay? Absolutely right. Fantastic. And that is, I just written it down with the 1 times the standard unit. And that is also the SE, if you like, the SE of sample, the standard error of sample 1 and standard error of sample 2. And here we set the standard error of sample 2, that was 1 over square root 3. And here we had 2 over square root 3. This is where this 1.15 and 0.577 come from. Okay, so good, so far, so good. Wasn't terribly challenging. Now, let's do something weird. Let's add sample 1 and the volume from sample 2 together. So what do we get? Sample 1 and sample 2 together, 100 milliliter, 40 milliliter. What do we get? And that is not a trick question.
Daphne.
Daphne. Look, you're absolutely right. We get 140 milliliter. Absolutely right. And you think, how bizarre. Of course we get 140 milliliter. But what is our uncertainty? What are we going to do with the uncertainty? Plus minus uncertainty. And what is this uncertainty? Salil already gave a solution for this uncertainty. And would be interesting to see how I think I figured out, I figured out how you calculated this resulting uncertainty. Nice try, really nice try, because what you did was you actually added the two uncertainties together. So you said 115 plus 100 plus 0.577. Is that right? Is that how you calculated it? Do you multiply them together? Do you add them together? Good questions. What shall we do with them? How do we get this new uncertainty? And this time, it is still a standard uncertainty, but it is now what is called standard uncertainty. Very often it is called SUC. And the C stands for standard uncertainty combined. How are we going to deal with that? Shall we add them together? Shall we multiply them? Well, none of them. Let's think about it. The uncertainty, the standard uncertainty for sample 1, we can see that sort of as going like almost like a vector. So it goes in that direction and has a certain length. That is the standard error for our sample 1. Okay, and this to use the biggest one. Now, this is our standard error or standard uncertainty for sample 1. And we also have sample 2. And the sample 2, it goes in a different dimension. It goes like that. This now is the standard error for our sample 2, the pink one. It goes in different directions because they are different samples. They come from different samples. And what we need to do is we need to find the sum of these two vectors. So what we need to find is actually the sum, this blue one here, of these two vectors. That is the sum of SE1 and SE2. And I can hear an acoustic feedback coming up. Thank you. So how can we calculate this combined? That is our standard uncertainty combined. Yes, Pythagoras. Exactly, you got it. So what we would do is we would calculate SUC equals SE1 squared plus SE2 squared and the square root of that. Yeah, do you see how I got that? It is the Pythagoras. It is a rectangular triangle here. That's a rectangle here, or 90 degrees. And I just simply apply the Pythagoras. And all I need to do now is calculate it as the standard uncertainty combined is the standard square root of the standard uncertainty 1, that was 2 over square root 3 squared plus 1 over square root 3 squared. It's not terribly difficult to do that. So I can square the first bracket, and that would give me 4, 2 squared divided by square root 3 squared, that would be 3, plus 1 squared, that's 1, divided by square root 3 squared, that again is 3. So that gives me square root, they have both the same denominator, so I can write that on the same denominator. 4 plus 1 gives me 5, so I get square root of 5 over 3. So we use the Pythagoras to calculate the standard combined uncertainty. Absolutely bang on. So that gives me square root of 1.67, and that is 1.29 or something like that. So that is our standard uncertainty. Absolutely right. Yes, what I have done is I just simply, instead of putting in the decimals for the standard error, instead of putting in 1.15, whatever it was, 5, I put in the actual, the ones that I calculated here with the standard error, because it makes it much easier with a calculator. So you can do either way. I just prefer it this way because it's so much easier. And you exactly, Kelvin's absolutely right. You get exactly the same thing. And this combined standard uncertainty is exactly, again, thank you for reminding me, is in the same units because it's in milliliter again. So how would we report our result? We would report it as 140.0 plus minus 2 times now our new standard combined uncertainties. So again, that gives us the 95% coverage. That gives us this wide range that we are looking for. That gives us an extended combined uncertainty. It's no longer standard, it's extended. And we can just simply calculate that. That would give us 140.0 plus minus 2 times 1.29. That gives us 2.6 milliliter. And that is how we would report it. Does that make sense? Yes, we would. It gives us 2.58, but remember, we would only, thank you very much. Oh, there's something more coming, don't you worry. 2.6 milliliter, because we would only report it to 2 significant figures. Okay, and this 2, again, that is to give an extended uncertainty. If we just report it with this one here, this is just then a very small, how shall I say, a small range that we get, and therefore it is conventional to report it by factor 2 or 1.96. So you would report it to 2 or maximum 2. No, let me start this sentence again. You would report it to usually 1 or maximum of 2 significant figures. Absolutely right. So you report this to 2 significant figures, and then you adjust the decimals. So here you have 1 decimal place, and you adjust the measurand here to the same number of decimal places. Okay? So we would have 140.0 plus minus 2.6 milliliters. So neither multiplied nor divided. Instead, we use Pythagoras. Right. And as I said, I promised you, we do something really weird. We had sample 1 plus sample 2. When we combine samples, we extended combined uncertainty, absolutely right. When it's a single, yes, absolutely right. Absolutely right. if we combine samples, it is a combined standard uncertainty. Okay, let me do it this way. If we have a single sample, single uncertainty, this would be a standard uncertainty. We can extend it by usually factor 2, then this would be an extended uncertainty. It's no longer a standard. By multiplying, it lost the status of standard. If we have two samples, two or more samples, we get a combined standard. And if we multiply it by 2, we get an extended combined uncertainty. No longer. What if we multiply samples? That is a totally different story. And we are not going to discuss that for the time being. What I instead want to discuss with you, we have sample 1 plus sample 2, right? What about sample 1 minus sample 2? The adjustment with the decimal places and the significant figures is what you do right at the end. That is really the last step. When you combine the uncertainties, you do the uncertainty, combining the uncertainties first, then you calculate the extended combined, and then you make the adjustment. So sample 1, that was 100, and that was 40. What do we get? Of course, we get 60 milliliter, but what do we do with our uncertainties? Do you invert the direction? That's an interesting thought. I have not thought about that. What you actually do is you use exactly the same principle. That's SE1, and that is SE2. You do a combined plus minus combined uncertainty. So again, you use Pythagoras. So that would be the SUC, and that is square root of SE1 squared plus SE2 squared. And we've just done that. This is actually what we just calculated here. That was square root of 5/3 equals, I just need to look it up, 1.2, 1.29 milliliter. What a lot of people find really, really challenging is that they say, right, when we add these samples together, okay, I get it that we have to add these standard uncertainties here, or the squares of the standard uncertainties, because we add the samples. Where a lot of people really struggle is that when you subtract the samples, again, you add the squares of the standard uncertainties. Because a lot of people would say, well, you take away something, so surely you would subtract the standard uncertainties from each other. But it's not the case. It is you add them. The reason why you add them is in the Pythagoras here. Does that make sense? So we would report here our result of the taking away pretty much as 60.0 milliliter plus minus 2 times this one here, 2 times 1.29 milliliter. And again, the 2, that is an extended. That's from the extended. And this bit here is the extended combined uncertainty. And we would report this as 60.0 milliliter plus minus 2.6 milliliter. And again, we report it to two significant figures here. That's two significant figures. We have one decimal place, so we would adjust our measurand to one decimal place. Does that make sense to you guys? Obviously, we would need to do a little practice on that. This is actually the case when we have addition and subtraction. When we have multiplication, you would not use these absolute standard uncertainties. You would use what is called relative standard uncertainties. But that is something that I'm going to show you next term when it fits better. So the reason why I introduced this concept is really this bit here, the standard combined uncertainty equals, and let me write this down again, standard error squared plus the standard error of sample 2 squared. Because this is actually, yes, exactly, the relative uncertainty is the percentage uncertainty. You're absolutely right. This thing here which derives from Pythagoras, as we just discussed, this equation here, believe it or not, I can do that. Yeah, it's therapeutic. This equation is the basic of all statistics that you have learned. So if you've learned a t-test, for example, this green bit here is actually the basic of statistics, of statistic testing. And that's why I wanted to introduce here. Very good question. Could it be more than 2 samples? Absolutely right. You can combine as many uncertainties as you want. So for example, if you have 2 samples, or if you have 3 samples, or if you have 4 samples, you can always combine them in that way. And for populations, you wouldn't use that because you are dealing with samples. Does that make sense? Oh my God, it's already 3 o'clock. It's time for my afternoon nap. So I'm going to stop here. Oh yes, you can combine it with equations. The equations are actually nothing for the faint-hearted, but you are not going to do that in your degree program. So thank you very much for watching. I will send you via email the link to the quiz website and also the practice calculations. And I would really encourage you to do that next week, because next week we are not going to have any lectures together. So you have a little bit of respite from me. And the week after, in week 8, I'm going to start on a slightly different topic. We are going to start on acids and bases and pH. So it would be great if you could have a look at that stuff from your school notes or from GCSE. So with that, I say thank you very much, and I hope you have a lovely and relaxing weekend and enjoy yourself, and don't do anything I wouldn't do. Take care. Bye-bye.